Hi students, welcome back. This is your last lecture in the Crustal Deformation series. So today, or this time, we are talking about earthquakes. All right, so first things first, what is an earthquake? So an earthquake is any kind of shaking of the Earth's surface that is caused by a release of energy. Okay, so most of the time this happens when faults rupture. They cause a lot of ground shaking as they release what we call seismic waves. And so on Earth every day, there are tons of these things happening. So earthquakes that we actually feel may not happen all the time, and the ones that cause the most amount of damage are not as frequent, but every single day there is an earthquake happening somewhere on Earth. Okay, so when we look at an earthquake's anatomy, we have a couple of things that we're going to talk about. So we have the fault, which actually moves the rocks, right? So that is what we talked about in the previous lecture. Faults rupture from plate tectonics, and when those faults rupture, they release some sort of energy, and that energy is released as what we call waves or seismic waves. So this energy is transmitted through the ground, through the crust, and it's what is causing most of the ground motion that you feel. Okay, so a couple of other things that we will talk about is the epicenter and the focus. So the epicenter is what's always on the news. It's the origin of the earthquake at the Earth's surface. And so a lot of people think that the epicenter is actually where the fault ruptured, and it's not necessarily true. Where the fault actually ruptures is what we call the focus. So the focus is the origin of the earthquake at depth. Most of the time, if these are superficial movements and they're actually moving at the epicenter, very close to the Earth's surface, they're not as strong. The deeper these earthquakes occur, the deeper the focus is, the stronger the earthquake actually becomes. So when we look at seismic waves, these are waves that move through body of rock, through the crust, that are released when the fault actually ruptures. Okay, we can pick these up on machines and get something like this seismogram here that actually shows us where all the waves are. And so we have body waves and we have surface waves. So body waves are the interior waves that usually arrive at a seismic station first. And then surface waves are what come kind of rolling after, and they are on the surface, and that's what you actually feel. And so the body waves are primary and secondary. We have P waves and we have S waves. The primary wave moves in a compression motion, and the S wave moves in a shear motion, so kind of like a snake. The surface waves that are on the surface of the Earth are called Love and Rayleigh waves, and they are a combination of both the P and the S wave. Okay, so how are they measured? They are measured on what we call seismometers. So seismometers, or also called seismographs, the seismometer is the actual meter. They are also called seismographs. These are stations that are set up in strategic locations to pick up these seismic waves, and they are recorded on a piece of paper that is spinning. It's kind of like a lie detector test. It makes motion when you get really nervous, right? So when these waves pass through, the needle point on the piece of paper actually moves and records how strong those seismic waves coming in are. And then the graph that you get at the end that was previously pictured is called a seismogram. I know that graph makes it sound like it should be a graph, but it's a seismogram, kind of like a telegram, and before we had real telephones. So this is what would record an earthquake, and we would have these or we do have these at specific locations around the world, and it helps us decide how strong an earthquake was, or figure out how strong an earthquake was and where it originated. So first, looking at P waves, like I said, these are your compressional waves. So here, you can imagine if you took a slinky and gathered a bunch of the wires together and then released it forward, that's the kind of motion that a P wave is creating. So you can try this at home with a slinky if you have it. There's also some videos that I will link in your lab that kind of show you this happening. P waves can move through solids, liquids, plasmas, and gases, and they tend to have a lower amplitude when they arrive at the seismic station. And so they move pretty quickly, but they don't amplify very strong. So we don't necessarily see a huge spike on our seismogram of the waves when they actually arrive. So they are faster than the P wave, which is why they're called the primary wave, the S wave, which is why they're called the primary wave. They arrive first at a seismic station, and they're the faster wave, but they're lower amplitude. Okay, moving on to secondary waves. These are a little bit slower than our P waves. This would be like if you took, this isn't a slinky, but you took a rope or a slinky and you moved it back and forth like this in an S shape. That is the motion that is being created here. So they only move through solids, so it makes it much more difficult when they encounter any other type of material. And they are slower than a P wave, like I said. They arrive last or secondary, which is why they're called the secondary wave, to the P wave at a seismic station. But they do create much stronger ground motion, so they are a much higher amplitude. So when you see on a seismogram, the waves kind of peak up real high, that's when you're starting to see a secondary wave or the S waves show up at the seismic station. Okay, so the combination between the P and the S waves creates our surface waves, which the first one is a love wave. The love wave has more of a horizontal motion, and it moves forward. And it is faster than the relay wave, so it is more of a combination between the S wave's motion, but the P wave's ability to move through material. It does move through solid materials only, so any kind of rock, you're going to feel shaking from a love wave. With a relay wave, they move a little bit more of an undulating up and down. So in a lot of movies, they like to show the relay waves on a very extreme motion where it looks like there's water waves being made out of the ground, basically. But it's not as extreme as that. And this motion that they show even in this little video is a little bit exaggerated. But it's a lot like an ocean wave, which is why that's what it looks like. It travels through solid material only as well, and it creates a lot of our ground up and down motion that we feel. The love wave is more of the side-to-side feeling that you feel. So when these arrive at a seismic station, they will start showing themselves on a seismogram. And so this is an example of one. You'll work with some in lab as well. And you can see where the P wave peaks up. So we have the 0 marker, and then we have a few waves start to show up. Those are the P waves. When they get much bigger, those are the S waves. And then sometimes the surface waves and the S waves actually come in tandem, and so you can't necessarily see a big difference between them. But here, there's a distinct difference between the S wave arrival and the surface wave arrival. But oftentimes they're found really close together, and so the S wave and the surface wave are the big peak that come up. But the P wave and the S wave, there's usually a big difference between the two. And depending on how big that difference is, it tells you how close you are to the epicenter. So since the P wave is faster than the S wave, if the P and S waves are moving just a mile, they might have a difference in time of 1 second. But if they go 2 miles, it might be 2 seconds. So as you get further from the epicenter of the earthquake, the difference between the P and the S wave arrival time increases. Okay, and we call that time difference the lag time of an earthquake. And so the lag time will tell you something about how close you are to the epicenter and how strong your earthquake was. So if you look at these 3 different seismograms, A, B, and C here, they are plotted on this PS curve relationship chart. And the 11-minute interval is further from the epicenter than, for example, the 3-minute interval lag time for seismogram A. Between A and C, there's a big difference there, right? And the distance is shown from the epicenter that with that increase in lag time, you have an increase in distance traveled from the epicenter. Okay, so then we can do some triangulation. And if we have 3 or more seismic stations that have recorded a particular earthquake, we can plot those on a map or on the globe and determine where the actual epicenter of the earthquake was. And then we can figure out what fault it came from. If we know about the fault, we don't know about the fault, then we start learning more things about that area. So seismologists who study earthquakes, they need at least 3 seismic stations or seismograms in order to triangulate the epicenter. Because we have really good technology nowadays, we have a lot of these stations set up, so we definitely have more than 3 that can pick up these things. All right, so one of the things that we talked about when we first started talking about the Earth's geosphere was what the different layers of the Earth was, what they were. So we know that there's the crust, the mantle, the outer core, the inner core, and what their consistency is, whether it's solid, a liquid, etc. So one of the big ways that we know this information is from earthquakes. So seismic waves will transmit through different materials a little bit differently. And when we start looking at that data, we can figure out what's actually happening below the ground surface. So for example, this is an image in the upper right of Yellowstone National Park. So the map is at the top, and then all of that orange is magma that's actually below the surface and tells us something about where we're going to actually see magma volcanism in the area. So you can see that plume is huge in comparison to what it's actually shown at the surface. So if we only used the information we have at the surface for Yellowstone, for example, we wouldn't know its actual capability looking at that giant plume. And we can see that through seismic waves moving through that material differently than the actual solid rock that is around it. And so this has also helped us in California to tell us something about what's happening below California and the Pacific Northwest area. Because if you take California geology, you would learn that the Farallon plate used to subduct beneath North America, and now there's only a remnant of it called the Juan de Fuca plate left. And so geologists did some studies looking at earthquakes and seismic waves underneath California, Oregon, and Washington to kind of get an idea of what the Juan de Fuca plate was doing. And one of the things that they did actually see is that there's a pretty large chunk, that gold chunk there in the center that's called accumulated asthenosphere, that is actually very buoyant and is pushing upwards. And so some of the uplift that we see in the mountains along the east side of California, the Sierra Nevada, and through Oregon and Washington is actually from this buoyant material actually pushing up on that and uplifting it. So looking at seismic waves through the earth and looking at what density of materials they are moving through is called seismic tomography, and we can kind of create these really cool 3D models to tell us something about what's happening below the surface. All right, so when an earthquake actually occurs, we want to know something about the magnitude and intensity, and the energy that is released will tell us something about that. And so depending on the information that you have, you're going to see a couple of different scales. And so there's 3 different scales that have been used. There's the moment magnitude scale, the modified Mercalli scale, and the Richter magnitude scale. The Richter magnitude scale is a lot more popular. It gives us that number from 1 to 10 that everybody is interested in. Was it an 8.0 earthquake? Was it a 5.5? And this was created by Charles Richter. The modified Mercalli scale is qualitative, so it doesn't give us a number. It gives us a scale based on felt effects, and we'll talk about all these individually. And then moment magnitude scale is the most accurate, but it takes a lot longer to calculate than the Richter scale. It does give us a quantitative number, but like I said, it takes a while to get. So when an earthquake happens, the immediate number that comes out is the Richter magnitude number. And then eventually they'll do some recalculations and make sure that they have the correct information and give you the moment magnitude. So looking at moment magnitude, we're going to see a lot more earthquakes at that lower number there. And then as you go up, you see less earthquakes, you see magnitude increase, and you also see the energy released is increasing. And so with a higher magnitude on the moment magnitude scale, you're going to see a higher energy release. It's a logarithmic scale. So it is similar to Richter as well with the 1 to 10, where the energy released is 10 times each scale it jumps. So a magnitude of 3 is 10 times larger than a 2, which may not sound like a lot, but it kind of is if you start looking at the energy released over there. It jumps up pretty significantly from a 2 being 123 pounds of energy released to a 10 being 123 trillion. So it is a big jump, even though it doesn't sound like, oh, it was a 2 or it was a 3 on the magnitude. It's a huge energy release difference between the two. But before we knew a lot about the energy and being able to calculate and create some sort of number to mean something for these earthquakes, we used the modified Mercalli scale. And so this is more of a did you feel it scale. What did you feel? What kind of structural damage occurred? And so this is directly related to the ground shaking intensity, not necessarily the energy released in the earthquake. So what was felt at the surface, what kind of damage was caused, and it gives you a scale there that you can, try to decide where you kind of fit. Did stuff fall off, just your shelves? Did your whole building collapse? Things like that. And you can, if you were in an earthquake of any kind, you can go to this USGS website and give your experience in the earthquake. And they make their own modified Mercalli intensity for whatever earthquake it was that you were in. And it's usually pretty close to what the Richter or the moment magnitude end up being. But it doesn't actually give you a numerical number to kind of go off of. But you can input your data there if you ever experience an earthquake. All right, and then looking at Richter magnitude scale, like I said, this one is the quick, fast, and dirty scale that we use. It's really quick, but it doesn't require a ton of calculations, and it is also logarithmic. So ground shaking increases tenfold for each magnitude you go up. So from a 1 to a 2, a 2 is 10 times more energy released than a 1. Okay, so here we use the amplitude and the interval between the P and the S wave to triangulate what magnitude we think might be from this earthquake. So here it shows you that there's an amplitude of 23. So on your amplitude chart, you would find where 23 sits, make a point, and then your PS interval is 24 seconds here. You would find that on the yellow far left chart. Find your 24 seconds, and then you just draw a line between the two, and wherever it hits the Richter magnitude, that's your scale. You'll do this in lab, and I do have a video showing you how to apply this if you get a little bit confused on determining your magnitude. You will determine an epicenter as well. All right, so here is a list of the 20 largest recorded earthquakes on Earth. This is updated in 2019 by the USGS, and then the map shows you where all those earthquakes have taken place. Where are all those earthquakes? They are around the Ring of Fire. They're around the Pacific Plate. So the Pacific Plate is subducting in a lot of different areas around the world, and the Pacific Ring of Fire is where we see a lot of volcanoes on Earth, and it's also where we see some of the largest earthquakes on Earth. Okay, down there in the bottom right, it shows you some Richter magnitudes and some seismic energy release, and as you can see, as you go up to the strongest earthquakes, which would be Chile, it has the highest magnitude and the highest amount of energy released. And so this is only the recorded earthquakes, right? This is anything that's happened since about 1900. Anything that happened before that, we don't have good record of as far as being able to measure the energy released and calculate a good Richter magnitude or even a moment magnitude scale. All right, so what controls the ground shaking? How much you're going to feel? So we've already talked about more energy release. That's obviously going to increase the amount of ground shaking you feel. The distance, so the closer you are to the epicenter, the more ground shaking you're going to feel. But then also, depending on the geology below your feet, you're going to either feel more ground shaking or less ground shaking. If there are loose soils below your feet, you're going to feel more ground shaking. If you're on solid granite, it's going to be less ground shaking. Why is that? Well, that is because seismic waves move through different materials differently, and through bedrock, there's less amplification. So as seismic waves move through bedrock, they don't amplify nearly as much as they do through something like unconsolidated materials like sediments, bay mud, things like that, water, there's a lot more amplification of waves there, and so they bounce a lot more. So think of the difference between jello shaking and shaking some concrete. Shaking concrete, it's really solid, it's not going to do as much shaking, but with jello, there's a lot of movement, right? So think of that when you're thinking about the seismic waves moving through different materials. Okay, so if we look at these two seismograms that are here, there's one where there's waves that are very highly amplified and some that aren't. So the bottom one there is a much lower amplification. Do you think that one is from poorly unconsolidated materials or bedrock? That one would be bedrock, so there's less amplification. The top would be something like unconsolidated materials, and so you see more amplification of the waves. Some other things that happen in tandem or as a result of earthquakes can cause just as much damage as the earthquake itself. Land elevation changes happen almost always when we are looking at dip-slip faults. So they move vertically, right? So there's some sort of vertical offset, and oftentimes that stays in place. And so there's a land elevation change. If that's right underneath a building, that's not good, right? Liquefaction can also happen, and this is when the soil loses its strength and stiffness, and we have a lot of water come up and basically creates this quicksand material at the surface, and it encompasses a lot of different things like cars and buildings and things. And then as soon as the earthquake is over, the water, which came from the groundwater, goes back down into the groundwater levels, and it regains its strength and stiffness. And so now all of those things that got kind of stuck in the quicksand are solid, stuck in that material. And so you have to come and dig all of those things out, which isn't a lot of fun. If it's a car, it's a little bit easier to do, but if it's a whole building, you've got a lot of work to do. Tsunamis also come as a result of earthquakes, especially if these earthquakes happen below the ocean. So this happens a lot in Japan because Japan is a very small island, but there's a lot going on underneath that. I have a diagram here in a little bit to show you that. And when that happens, that displacement of water as the fault ruptures, the water has to go somewhere. So that water ends up creating these large waves, and those waves end up hitting coastlines. So if there's ever an earthquake over in Japan, California typically gets a tsunami watch or warning, depending on how severe the earthquake was. And then last but not least, landslides. So slope failure from ground shaking can also occur, especially if that material was already weak and was losing its integrity at the time. Any kind of ground shaking is going to loosen that material and make it go down slope. So when all of these things happen, we see a lot of destruction, right? So a lot of our building materials cannot withstand earthquakes, especially at high magnitudes. And so depending on the flexibility of your material, you're going to see a lot of damage. The most devastated that we see is unreinforced masonry. The wood framing is usually the most likely to survive. And then steel is really good in its ability to move elastically before it fails. So if you're an engineer or an engineering major, you would be most interested in some of these things and diving into which type of materials you would want for your building, depending on where you are building that building in California or elsewhere. And if you need something that's going to actually go in, let's say, resonance, which matches the frequency of the earthquake so that it's less likely to fail. And all of those things go into engineering design, especially if they know that they are on a fault zone. So in the coast ranges of California, we have a lot of specific design criteria that have to be followed in order to meet the resonance requirements and the intensity of the earthquakes that can happen along the San Andreas Fault, the Calaveras Fault, the Hayward Fault, the Northridge Fault, all the faults that run up and down the west coast of California. All right, so we talked about plate tectonics causing faults and faults causing earthquakes. And so if we look at a map of our tectonic plates, we kind of already talked about this a little bit. You can also look at a map of the seismic station or seismic map of the world and kind of see how they overlap. So as you can see on the left, the outline of the plates is approximately where all the earthquakes happen on Earth. And so this is why we know where the plates are, is from looking at earthquakes, their locations, their epicenters, and then you can basically do a little trace and see where all the plates lie. So let's look at plate boundary versus magnitude. So with divergent plate boundaries, they are pulling apart, right? They're experiencing tension. And because there's no rocks slamming into each other or really grinding next to each other, we see very small earthquakes. They're not going to be very large in magnitude. Usually they're less than 5 on the Richter magnitude scale. With transform plate boundaries, they're a little bit larger, so they can be about 7 on the magnitude scale. We have rocks that are sliding and grinding past each other, but it's kind of like bumping into somebody, right? It hurts, but it's not going to be super extreme. Whereas when we get to convergent plate boundaries, depending on whether they're continental collision, or they are subduction zone, where we have oceanic continental collision, they're going to be very large, 7 to 8, or colossal, larger than 9. So our largest recorded earthquakes on Earth actually happen from subduction zone boundaries, and that is because those earthquakes happen deeper and deeper and deeper in the Earth. So if you remember the Benioff zone from the plate tectonics lecture, that is what we're looking at here. The Benioff zone allows for earthquakes to originate deeper in the crust, and that creates much larger earthquakes on the surface. So here's a closer look at seismicity in the United States. So as you can see, most of the seismicity occurs along our plate boundary. There are a few earthquakes that happen throughout the country. And then we also have a lot in Hawaii because there's a volcano there. And then in Alaska, where we have the Pacific plate subducting beneath the North American plate in that region. Here's a look at the hazard. Again, we have a lot of hazard along the San Andreas Fault, along the Aleutian Islands, and then we also do in Hawaii. And the reason the seismic hazard is in Hawaii is because seismicity is just a measurement of ground shaking. And so earthquakes can come as a result of magma pushing up on the crust. And as magma pushes up on the crust, it creates some ground shaking on the surface. And so Hawaii does actually look out for earthquakes in addition to volcanism. In California, like I said, most of our hazard is along the coast where the San Andreas Fault transect is. There's also some hazard along the Garlock Fault, which runs through Tehachapi Pass, which is in Southern California there. It runs perpendicular to that San Andreas Fault, and then there is some going north on the east side there, which is the Sierra Nevada Frontal Fault System. Earthquakes, like I said, happen every day. So here is a map showing you in California the earthquakes that have happened in the last hour, day, or week, and it shows you their approximate magnitude. So the more small earthquakes we have, the less likely we're going to see a really big one. So that's one of the issues that we have right now in the southern portion of the San Andreas Fault, is there's not enough energy being released on a regular basis that warrants the amount of energy that should have been developed at that time. So we haven't seen a major earthquake in Southern California along the San Andreas Fault in over 200 years or so. And so we are overdue for one down there. And as soon as that happens, it's going to devastate that basin. So if we could see a more regular release in energy along the San Andreas Fault transect, we would see a less likely occurrence of a very large earthquake happening. But they're looking at something in the matter of 7 to 8 on the magnitude, the Richter scale. And like I said, it would devastate that region. They are not ready for it, even though they pretend like they are. Their buildings are not prepared. So here are some notable California earthquakes since 1970. There's lots of them listed there. It gives you a little bit of information on the loss of life and property, the location, and then their magnitude. But we'll talk about a few notable earthquakes. All right, so the San Andreas San Francisco earthquake of 1906. This one was how geologists discovered that there was a very large transect fault through California. And this was a magnitude 8.5, one of the largest recorded on the San Andreas. It's caused $400 million in damage in 1906. I don't even know what that is in 2023, but it's a lot. And that would be 700 to 800 deaths, which could have been a lot more, but there weren't that many people living in San Francisco as there are today. One of the really interesting things that came about this earthquake, not only discovering the San Andreas Fault, but they also tried to put it off as the 1906 fire. So there were a lot of fires, and that was from gas lines breaking. But they were trying to get people to come back to the area, and if people thought that an earthquake was going to constantly devastate the region, people weren't going to want to live there. So they marketed it as the 1906 fire, and so a lot of newspapers kind of made the earthquake seem like a lesser thing than the fire was. And it worked. There's a lot of people live in San Francisco and the Bay Area now, and all of them are living with this threat, right? There are some that have happened since then, but not nearly as damaging as the 1906. We also have the San Andreas Loma Prieta, which is, in the region, but not exactly in San Francisco. This was a 7.1 in 1989, $5.9 billion in damage, 63 deaths, 3,000 injured. Not as many deaths, which is good. We're getting a little bit better at protecting people. But still, $5.9 billion in damage. That's significant. And you can see the aftermath of this earthquake. We also have the San Andreas Northridge, which was a magnitude 6.7 in 1994. This was $40 million in damage, only 57 deaths, but 11,000 people injured, which puts a real strain on our hospitals, right? And now we have all of these roads that are closed that have to be repaired, a lot of bridges that were damaged from this earthquake. One of the more recent in California you might have felt was the Ridgecrest 2019 earthquake. This is a magnitude 6.4 and 7.1. They were consecutive earthquakes in the Ridgecrest area of the Mojave Desert. And there's not a lot of people that live over there, fortunately. But it did do quite a bit of damage to the structures because they weren't necessarily built like the structures are built in San Francisco or the Bay Area. And so you can see some of the offset there and the transect at the fault. One of the big worries here was that the earthquake in Ridgecrest could have initiated earthquakes along the Garlock Fault, which hasn't moved in quite some time, which runs through Tehachapi Pass in the southern Sierra Nevada area. But nothing happened, so that was kind of good. But this was one of the more recent higher magnitude earthquakes that happened in California. Then we have Japan. So I told you that Japan was kind of a problem child. There are 4 different plates interacting underneath Japan. We have the Eurasian plate, the North American plate, the Pacific plate, and the Philippine plate. Some of them converge, some of them are transformed. So between Eurasia and North America, they just kind of slide past each other. But the others are all converging against each other. And so that creates really large magnitude earthquakes in Japan. And so in 1995, there was a magnitude 7.2 in Kobe, $200 billion in damage, 5,500 deaths, and 26,000 people injured. You can see that freeway overpass there, or that elevated freeway there is completely destroyed, has to be cleaned up, repaired. It's kind of an undertaking when things like this happen. Another one in Japan in 2011. This was a magnitude 9. So this was much higher on the magnitude scale here. And the big thing that happened here was a tsunami. And so there was displacement underneath the water there in the Pacific Ocean, and it caused huge waves to come into the east coast of Japan, and we saw a lot of people die. So we have 15,000 confirmed deaths here, most of which were from the tsunami, not from the earthquake. 4,000 people missing, 130,000 displaced, and about $309 billion in damage. Then we get into the devastating stories of third world countries. So we just talked about California and Japan, which have significant earthquakes, but a lot of the engineering there is pretty well developed that even though there is a lot of damage, not everybody's left homeless. We don't have as many people die. But in places like Haiti, when an earthquake hits, it is absolute devastation. So this is the 2010 Haiti earthquake, which was a 7.0 magnitude, for $1 billion in damage, 170,000 confirmed deaths, and approximately 1.2 million people homeless. So why do you think their infrastructure basically all collapsed? You can see from some of these pictures, it looks like almost all of their buildings collapsed. It's because they don't have the engineering and the geology to back up when they're building something. Their infrastructure is poor in comparison to Japan and California. And so they need, if these things are going to keep happening there, which they probably will, they need help with designing their buildings so that this doesn't happen again and it doesn't devastate their communities. This happened this year in 2023 at the Turkey-Syria border. The fault there ruptured and caused a magnitude 7.8, and then another subsequent magnitude 7.6, I believe, a couple of days later. They had some pretty significant aftershocks, which were not like that area necessarily. We knew that there was a fault there called the North Anatolian Fault. That is a transform fault, just like the San Andreas Fault. But they have not experienced an earthquake of this magnitude in a very long time. So there is about $10 to $100 billion in damage estimated at this time. In Turkey, there was about 51,000 confirmed deaths, and in Syria, about 8,000 confirmed deaths. So it was pretty devastating. Same situation or similar situation to Haiti, a little bit better infrastructure, but still they were not prepared. So in summary, our earthquakes are being caused from fault rupture. They are a measurement of the release of energy from that fault rupture. They cause ground shaking, and that ground shaking is determined by the amount of energy released, the subsurface geology, and how close you are to the epicenter. The big takeaway here is that the earthquakes don't actually kill people. It's falling buildings that do, tsunamis, things like that. So earthquakes themselves don't kill people. If you are standing in a field and an earthquake happened, you're just going to fall down. But if you're in a building and the building starts to collapse, you could die. So think about that when you talk to an engineer. All right. I will see you guys in the next video. Bye.